Hello everybody, welcome to chapter 1.3. We're going to split this into two parts just like we did 1.2. Today what we're going to talk about is evaluating a limit using properties of limits, which we're going to discuss, and then how we're going to develop and use a strategy for finding limits. Okay, so let's get started. As promised, we're first going to talk about properties of limits. Pardon me. And first, what I'd like to kind of roughly define with you right now, the terms continuity, the concept continuity. Hang on one second. Sorry about that. The concept of continuity. And what you need to understand is that certain graphs, certain functions are either going to be continuous or discontinuous. And we're not going to define those in words just yet because we're really going to get into those concepts in the next chapter in 1.4. But what I did want to give you is kind of a visual of what this means. A graph is continuous if it does something like this. So say here's our coordinate plane. And say maybe we have something like a parabola, right? Meaning that it would never really stop. It would just continue in its domain forever. And then similarly, maybe if we have a graph similar to a sine function, right, where we have that curve that goes up and down, and it would continue on that path forever. That is another example of a continuous graph, where it goes forever in its domain. It's defined in all of its domain, and it is essentially uninterrupted is the way you can think of it. A graph or a function can be discontinuous if it does any of the following things. If, for example, say that there's a hole in your graph, so say we had our coordinate plane and then here's our graph and there's this hole in it. And sometimes we can refer to this as discontinuous or, removable discontinuity. But again, don't worry about that too much right now. We are going to go more in depth with the removable concept in the next chapter. But what's important to realize is that when there's a hole, it's discontinuous. When we have a graph that does a jump, right, where it's at a certain point, and one of these could even be filled in, where it's continuous, and then it jumps and goes to another value. And again, we'd call that a jump. Another example of discontinuity is when there's a gap in your graph. So we'll draw another example of what that means. Maybe something like this, where each separate piece would have been continuous, but together this function is not. It jumps from this graph to this graph. And we call that a jump. And then another example, last basic that you should know, is an asymptote or infinite discontinuity, where at a certain point in the graph, the x values just go continuously in the same direction, but they never approach the same y value. Okay. Moving on. That's the basic concept of continuous and discontinuous. Now, if we're going to use this to help us, First, we're going to talk about direct substitution. And we can use direct substitution for functions that are continuous at the c value that we're trying to find. Then we can assume that the limit as x approaches c for f of x is the same as f at that value. Again, when we know there's nothing crazy going on, when we know there's no holes, no jumps. Oh, pardon me, I called this the wrong thing. This should be gap. Change that in your notes. Gap, and then infinite. If there's nothing crazy going on, if it's a pretty defined and not crazy function or graph, then we know that we can just use direct substitution because the value at that point, the value it approaches, is the same as what it's equal to at that point. And here are some basic properties of limits that we should know. I know that I already wrote this title, just write it again, no worries. And here's the three that are important, again for those continuous functions at c. The limit as x approaches c for a constant is that constant. And the limit for the function x as x approaches c is just c, again for those continuous functions. And lastly, the limit as x approaches c for the function x to the n is the same as c to that same n value. And here's a quick example of what all of those mean. So, for example, with some numbers, the limit as x approaches 2, the value of 3 is just the same as saying 3. And the limit of x as x approaches, let's say negative 2, well, again, we can just say that that's the c value, or negative 2. With this last property, the limit as x approaches 4 for the value x cubed is the same as saying 4 cubed, or 64. Okay. Excuse me. Excuse me. Some other basics we should know. We'll continue on another page. We need to specify a little bit there. For the next set of properties, we can use two functions, and we're going to define those functions really quick. The following properties work if the limit as x approaches c for f of x equals L, and if the limit as x approaches c for g of x equals k. Then we can have the following properties. The first we can call the scalar multiple, and this property says that if we have a limit as x approaches c of b times f of x, that's the same as saying that same b number times the limit itself. The next one we have is the sum or difference property. And what that one says is if we have a limit as x approaches c for the function f of x plus or minus the function g of x, that's the same as saying the limit of f of x plus or minus the limit of g of x. And the last, not the last one, pardon me. The next one we'll say is product property. We have the limit as x approaches c for the function f of x times the function g of x is the same as saying the limit of the first times the limit of the second. That's the product property. The quotient property says that when we have the limit as x approaches c for f of x over g of x, we have the limit of the first L over the limit of the second K. And last one we have to talk about is the power property, where if we have the limit as x approaches c for f of x to the n, we have that limit to the n. All right, let's go through some examples and let's use some of these properties we've just discussed. So, for example, let's talk about limits. The limit of a polynomial. So, say that we had the example, the limit as x approaches 2 for the polynomial 4x squared plus 3. What we get to do here is recall the property we just discussed, the sum or difference property up here, where if we have a limit as x approaches c for f of x plus g of x, it's the same as saying the limit of f of x plus the limit of g of x. Okay, so let's utilize this. And let's plug in the appropriate things. So we're taking the limit as x approaches 2 of 4x squared plus 3. And we can break that up first as saying the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. And if we apply some of our properties, we know we can take that 4, factor that out, and then take the limit as x approaches 2 of x squared, and we can use direct substitution here, plus the limit as x approaches 2 of 3. Again, if you recall from those first properties we talked about, whenever we have x squared, we can just take the c value and put it to the same exponent. So we're going to say this is the same as saying 2 squared. And then if we have a limit of a constant as x approaches any value, our limit is just that constant. So our limit here is 3. And when we multiply, 2 squared is 4, 4 times 4 is 16, and then 16 plus 3, that's going to get us 19. And there we go. We've taken the limit of a polynomial. The next topic we're going to discuss is, let's get another sheet of paper here, the limit of a rational function. Now, if we're going to deal with yet another property, but first we have to specify that if a rational function r of x equals p of x over q of x, And C is real such that if we plugged in C to the bottom of our fraction, if we did Q of C, and we didn't get 0, then we can use the following property. The limit as x approaches C of R, oh, that's an R, of x is the same as saying R of C, which is the same as saying P of C over Q of C. All right, and we're going to use an example to help us really conceptualize this property. So for example, if we were asked to find the limit of, as x approaches 1, of the function x squared plus x plus 2 all over x plus 1, we can see right away that this fits our condition. We have a rational function. Excuse me. C is 1, so it's a real number, and if we plugged it in to our bottom, our Q of x, if we plugged it in on the bottom, we would not get 0, so we can use this property. So we can set it up as R of C, right? Plugging in R1 for every x that we see here. We can just plug in for P of C and Q of C. So we're going to do P of 1 and Q of 1 down here. We have 1 squared plus 1 plus 2 all over 1 plus 1. When we start to simplify things, we get 1 squared, which is 1 plus 1, which is 2 plus 2. And then on the bottom, we have 1 plus 1, so we get 4 plus 2, pardon me, 4 over 2, which is just 2. Okay. And that's the limit of a rational function. Let's talk about the limit of a radical function. Of a radical function, or of a function involving a radical. And the property we can use here to help us out is as x approaches C, for the function x to the n root of x is equal to the n root of C. And in order for this to work, we have to meet the following conditions, where n is a positive integer, and it's valid for all C when n is odd, and then it's valid for C greater than 0 when n is even, which makes sense because we know we cannot have a negative number, a number that is less than 0, in an even root. And let's see, another property we should talk about are the limits of a composite function. And first we're going to specify. So if f and g are functions such that the limit as x approaches C for g of x equals L, and the limit as x approaches that L for f of x equals f of L. then we can say that the limit as x approaches c for f of g of x equals f of the limit as x approaches c of g of x is the same as f of L. And this makes sense because we're essentially undoing the limit of the g of x, right? Because limit of g of x equals L, and we can sort of substitute this whole piece in if we know that this limit equals f of L. Well, f of L is just f of this thing. Using equations, it's how we can substitute everything in. And let's do an example of a composite function. So, we're going to say that because the limit as x approaches 0 for the function x squared plus 4 is equal to 0 squared plus 4, which would then just be 4. And the limit as x approaches 4 for the square root of x is equal to the square root of 4, or just 2. We can conclude that the limit as x approaches 0 for f of g of x for the square root of what's inside here, x squared plus 4, is equal to the square root of its limit, 4, which is just 2. Okay. And the last thing we have to list out here are limits of trigonometric functions. I know we don't actually say it like that. I just like to say it while I'm spelling it out. It's actually trigonometric if you say it quick. And it looks like we got 1, 2, 3, 4, 5, 6. We have 8 properties. We got 8 properties, but they're all pretty short, so hang tight. We've got the limit as x approaches c of sine of x is equal to sine of c. Again, a direct substitution, because as we know, if we look back to what we first drew with continuous, we've got something just like a sine curve, right? It's completely perfectly continuous, so we know that we can use that direct substitution in here always. There's never going to be any holes, jumps, gaps, or asymptotes in a sine curve. And similarly, the limit as x approaches c for cosine of x, same thing, cosine of c. Direct substitution is okay with our trigonometric functions. And if we keep going on this thread, you guys, guess what? Tangent works the same way. Tangent of x, direct substitution, is the same as tangent of c. Secant, the limit as x approaches c of secant of x is the same as secant, let's put parentheses in here, of c. Cotangent, the inverse of tangent. Oh, pardon me, that is not the inverse of tangent. Forget that I said that. Arctangent is the inverse of tangent. Got carried away, pardon me. Cotangent of x is the same as cotangent of c. When we're taking the limit, we can just direct substitute in our c value to find the limit. Let's see. Secant. Oh, we already did secant. What am I missing? Oh, here we are. The limit as x approaches c for cosecant of x. Again, direct substitution. Last two, we've got Also, our natural logarithm, ln of x, we can direct substitute in with this function as well. And lastly, our exponential functions, so limit as x approaches c for a to the x is the same. We can find the limit by just plugging in that c for our x, and this applies when a is greater than 0. Okay. And let's see. Those are really all the properties that I have to show you. We'll do a few examples using these properties. So the first one, say we wanted to know the limit as x approaches 0 for sine squared of x. Well, what we can do is we can sort of take that squared and remove it out. So we can say the limit as x approaches 0 for sine of x squared. Well, now we have something we can use direct substitution with. So we can say the limit as x approaches 0 for sine of 0, which we know to be just 0 squared. So we can say sine of 0 is just 0, and we still have 0 squared, but we know that that's 0. Okay. Again, I'm going to use a color to outline what I just did. This piece, the limit as x approaches 0 for sine of 0, well, we got to use direct substitution, so now we're just simplifying this part. Sine of 0 is 0. And so we get 0, and then we still have that squared, so we put the squared right there, and that's how we get 0 for our answer. The last example that I'll do with you guys is this. Say we wanted to know the limit as x approaches -1 for x outside e to the x. Again, we're going to separate this out into two easier to handle things. We have the limit as x approaches -1 for x. Again, we know we can use some direct substitution here. And the limit as x approaches -1 for e to the x. And that is also, again, going to be direct substitution. We talked about how natural logarithm is a direct substitution property. So when we simplify this, we can just call the limit here direct substitution and call this -1. And here we can also use direct substitution. So this is going to be the same as e to the -1. And now if we multiply these together, we're left with -1 times e to the -1, which is just -e to the -1. And that would be enough. The thing that I do want you guys to take away before I let you go from this video are I want you to recognize when direct substitution can be used to evaluate limits. And remember, it can be used in the following cases. With natural logarithms, natural logarithmic functions, with our exponential functions, with all of our trigonometric functions, with our rational functions like we talked about here, and with our polynomial functions like we talked about here. That is when direct substitution is totally, completely okay. All of these properties, all of rational, radical, and all of our trigonometric, all of these properties, these all say when it's okay to use direct substitution to evaluate a limit. So I do want you guys to start committing this to memory, get used to using these tools that you now have in your toolbox to help you evaluate limits. Okay, we'll see you in class tomorrow.